What if the most important stars in the universe are also the most ordinary, not the brightest, not the strangest, but the ones that quietly hold galaxies together with their long, steady light? In today's video, we're exploring main sequence stars, the stars that dominate the universe, including our own Sun. If you enjoy this kind of science content, don't forget to like, subscribe, and share. And thank you so much for watching and supporting the channel. Before we start, tell me in the comments what time is it for you right now, and where in the world are you listening from? And now, let's step into the story of the most common stars in the cosmos. A main sequence star does not begin as a star in the full sense. It begins as a region inside a cold molecular cloud, where hydrogen, dust, and trace heavier elements drift across enormous distances in thin, dark concentration. For long stretches of time, nothing about such a region appears urgent. The cloud remains diffuse, shaped by turbulence, magnetic fields, shock waves from nearby stellar events, and the slow pull of gravity acting across a volume so large that collapse can take an immense amount of time to gather itself into motion. Yet once a denser knot forms within that cloud, the quiet balance begins to fail. Gravity starts drawing material inward more effectively than pressure can resist it, and a contracting core appears inside the wider haze. That small change is the beginning of everything that follows. The future main sequence star is not yet shining through fusion. It has not yet reached the stable state that will define most of its life. But the path toward that state has opened, and from that point onward the history of the object is shaped by one central fact matter. Falling inward releases energy. As the cloud fragment contracts, gravitational energy is converted into heat. Density rises. The central region grows warmer and more opaque. Surrounding gas continues to fall inward, often through a rotating disk that forms because even a slight initial spin becomes more important as the structure shrinks. Jets and outflows can emerge along magnetic channels, carrying away angular momentum and helping collapse continue. The newborn object at the center is called a protostar, and it is already a real physical body with temperature, structure, and radiated energy. But it is not yet supported by the long-term engine that will make it a main sequence star. Its light comes mainly from contraction, not from sustained hydrogen fusion in the core. That difference matters because contraction is a transitional power source. It can brighten the object for a time, but it cannot hold the next stage back forever. The protostar is still changing too quickly, still adjusting, still carrying the instability of formation within it. Around young stars of modest mass, one of the most recognizable early phases is the T Tauri stage, a period marked by youth, variability, and lingering interaction with the surrounding material from which the star has formed. In this stage, the object can still be wrapped in gas and dust, still accreting matter from a disk, still driving energetic outflows, and still showing brightness changes tied to magnetic activity, surface features, or uneven accretion. A T Tauri star is not fully settled. Its interior is still contracting toward the deeper pressures and temperatures required for a more durable equilibrium. In astronomical terms, this stage is brief, often lasting only a few million years, which sounds long by human standards but is extremely short beside the far longer stability of the main sequence that may follow. The brevity is part of what makes the transition so important. A star spends comparatively little time becoming itself, and an immense amount of time being what it has become. The decisive change arrives in the core. As collapse continues, the central temperature climbs into the range where hydrogen nuclei can finally overcome enough of their mutual electrical repulsion to begin fusing into helium. This requires conditions of extraordinary compression and heat on the order of many millions of degrees. Before that threshold is reached, the protostar is always on the way to somewhere else. After it is crossed, the entire logic of the star changes. Energy is no longer supplied mainly by the release of gravitational potential through contraction. It now begins to come from nuclear fusion in the core itself. That new source of outward pressure transforms the structure from a body still falling into tighter confinement into one that can oppose gravity from within. The star has not escaped gravity. It has answered it. This is the turning point behind the phrase main sequence. Stars on the main sequence can differ enormously in brightness, surface temperature, radius, and mass. But they share this one foundational condition. Hydrogen fusion in the core has become the dominant energy source, and the star has entered a long period of relative structural stability. The transition is not a theatrical ignition in the ordinary sense. It is not a sudden burst that simply turns darkness into light. The protostar has already been radiating energy before fusion begins. What changes is deeper and more consequential. The source of support becomes internal and self-sustaining on stellar timescales. Inward gravity continues pressing every layer toward the center. Outward pressure from the hot interior continues pushing back. When these forces come into balance, the star reaches hydrostatic equilibrium. This equilibrium is one of the most important ideas in stellar astronomy, because it explains how a star can remain stable for millions, billions, or in some cases far longer than that. Without gravity, the gas would fly apart. Without internal pressure, the star would continue collapsing. What exists instead is a standing contest between compression and response, maintained every moment throughout the star's life on the main sequence. The result is the nearly spherical form associated with stars, not because they are perfectly still, but because their internal forces are organized into a durable balance. That stability is not passive, it is active, renewed continually by the conditions in the core. If the core begins to compress slightly, temperature and pressure rise, fusion tends to increase, and the stronger outward push resists further contraction. If the core expands too much, temperature falls, fusion becomes less effective, and gravity regains ground. In this way, the star regulates itself. The balance is not delicate in the everyday sense. It is robust enough to persist for spans of time that shape planets, atmospheres, and eventually the chemical history of galaxies. The Sun, which will appear later in this story as a middle case among stars, is in that condition now, quietly maintaining the pressure needed to resist its own weight through hydrogen fusion deep in its center. But the same principle applies across a wide range of stars. What changes from one star to another is how much mass gravity has assembled, and therefore how intense the core conditions become. In the earlier settled moment, once the T-Tauri stage has given way to core fusion and structural balance, the star takes its place on the main sequence. This is where most stars spend the overwhelming majority of their existence. It is also why the main sequence is not a minor category, but the central population of stellar life. To say that a star has entered the main sequence is to say that it has reached the long middle of its story, the stage in which its defining internal process can continue steadily for an enormous span. For the smallest stars, that span may exceed the current age of the universe. For larger stars, it may be far shorter, but in either case, the moment of arrival is profound because it marks the end of formation and the start of endurance. The young object that once flickered through an unsettled youth, wrapped in the debris of its own birth, now becomes a stable source of light. Around it, leftover disks may thin, planets may continue forming, and nearby gas may be illuminated by the radiation streaming outward from a star that has finally found a way to resist further collapse. The universe is full of such transitions, though any single one unfolds too slowly to watch in full. What can be observed instead are the different stages spread across different objects' dark, star-forming clouds, protostars still embedded in dust, T-Tauri stars marked by youthful instability, and mature stars already settled onto the main sequence. Together they reveal not a sudden creation, but a sequence of physical thresholds. Gravity gathers matter, contraction raises heat, youthful instability gives way to deepening pressure, core conditions cross the point where fusion can begin, balance replaces rapid adjustment, a main sequence star appears. That sequence is simple in outline but immense in consequence, because once hydrogen burning begins at the centre, the object joins the dominant stellar population of the cosmos. Most of the stars visible across the Milky Way, and most of the stars lighting galaxies beyond it, are in this long, stable phase. Their beginnings are restless, but their mature state is enduring. The strange fact is that such stability is born from collapse. A star becomes steady not by escaping inward pressure, but by falling deeply enough into it that a new source of power awakens at the centre. What looks from a distance like an ordinary point of light is therefore the outcome of a long negotiation between gravity and energy, youth and structure, contraction and resistance. The main sequence does not begin when a cloud first gathers, or even when a protostar first glows. It begins when the core becomes hot and dense enough for hydrogen fusion to hold gravity and lasting balance. And from that point the star enters the defining condition of its life. On a Hertzsprung and Russell diagram, where stars are arranged by brightness and surface temperature, the main sequence appears not as a narrow category, but as a long slanting band, running from hot, luminous blue stars at one end down to faint, cool red stars at the other. That visual pattern is one of the most revealing maps in astronomy, because it gathers stars that seem almost unrelated and shows that many of them belong to the same underlying condition. Some are far larger than the Sun, some are much smaller. Some flood surrounding space with intense radiation and burn white or blue at the surface. Others glow so dimly in red that they are nearly invisible without careful instruments. Yet despite those differences, they can still be called main sequence stars for the same fundamental reason in their cores. Hydrogen is being fused into helium, and that fusion is supplying the energy that supports the star against its own gravity. The term does not refer first to size or colour or visual impressiveness. It refers to the star's central engine and to the stable stage of stellar life built around that engine. This is why the category is so broad. A star can look very different from another star and still belong to the same sequence, because the essential definition lies deeper than appearance. At the surface, a star presents temperature, colour, brightness, and sometimes a familiar proper name. In the interior, what matters most is whether the core is hot and compressed enough to sustain hydrogen fusion as the dominant source of power. If the answer is yes, the star belongs to the main sequence. If the answer is no, then however bright or interesting it may be, it falls into another stage of stellar evolution. That distinction matters because stars do not remain the same forever. Before the main sequence, a young object shines mainly through contraction. After the main sequence, an older star may begin fusing different elements in different regions, or it may expand into a giant, shed outer layers, or collapse into a stellar remnant. The main sequence is therefore not simply a place on a chart, it is a particular long-lived phase in the life of a star, defined by the persistent conversion of hydrogen into helium at the centre. What makes this especially striking is how many stars live in that condition. The vast majority of stars observed in the Milky Way are main sequence stars, and the same is true across other galaxies. Their physical properties vary enormously, but the same deep process runs through them. That is why the phrase main sequence carries so much weight. It names not a special exception, but the ordinary state of stellar existence. The diversity inside that ordinary state comes mainly from mass. Mass determines how strongly gravity compresses the core, and that compression determines core temperature and pressure, Once those conditions are set, much else follows from them. A more massive star has a stronger inward pull, so its centre becomes hotter and denser. Under those harsher conditions, fusion proceeds at a much faster rate. The star becomes brighter, hotter at the surface, and shorter-lived overall because it spends its fuel quickly. A less massive star has weaker gravitational compression, so its core remains cooler by stellar standards and fusion proceeds more slowly. The star is dimmer, cooler, and far more patient in its energy use. Both are still main sequence stars as long as hydrogen fusion remains the governing process in the core. The difference lies in the pace and intensity of that process, not in the fact that it is happening. This is one of the central ideas behind stellar classification. Main sequence stars are not identical objects repeated across space. They are a family held together by one physical rule and diversified by how much matter, gravity has gathered into each member. Colour follows from that same story. Hotter main sequence stars tend to appear bluish or white because their surfaces radiate more strongly at shorter wavelengths. Cooler main sequence stars appear orange or red because their radiation peaks at longer wavelengths. The colour is not cosmetic. It is a clue to surface temperature, and surface temperature in turn reflects deeper structural conditions inside the star. But even here, the definition remains anchored in the core. A red dwarf and a blue giant on the main sequence may seem to occupy different worlds of stellar behaviour, yet both remain in the same broad category, because each is supported by hydrogen fusion at the centre. Their surfaces differ because their masses differ. Their luminosities differ because their fusion rates differ. Their futures differ because the rate at which hydrogen is consumed differs. Still, for the interval in which core hydrogen burning governs the star, they stand together on that long diagonal line across the stellar diagram. This is why the main sequence is best understood as a physical principle made visible. It is the outward appearance of an inward fact. The chart does not create the sequence. The shared internal process does. Once astronomers recognized that the stars along this band were not arranged randomly, but according to a meaningful relationship between brightness and temperature, the sequence became one of the clearest windows into stellar evolution. It revealed that stars are not merely points of light with arbitrary properties. They are self-gravitating systems whose observable traits emerge from a small set of governing conditions, especially mass and internal energy generation. The main sequence shows the long equilibrium between those things. A star on that sequence is using hydrogen in its core as the main fuel of its stable life. That sentence sounds simple, but it contains a great deal. Hydrogen is the most abundant element in the universe, and stars formed from interstellar clouds begin largely as hydrogen-rich bodies. Fusion converts a portion of that hydrogen into helium, releasing energy because the helium produced has slightly less mass than the separate hydrogen nuclei that went into making it. The missing mass is transformed into energy according to one of the most famous relations in physics. In a main sequence star, this conversion happens under enormous pressure and temperature in the core, and the energy released gradually works its way outward, first through dense interior layers and eventually into space as light, heat, and other radiation. That outward energy flow is what allows the star to remain stable over long intervals. It is also what makes stars visible across vast cosmic distances. But again, the visibility is secondary to the definition. A main sequence star is not defined by being seen. It is defined by the nuclear process maintaining its structure. This becomes especially clear when considering objects that are almost stars but not quite. A brown dwarf, for example, forms in a similar general way through gravitational collapse, but it never gathers enough mass to raise its core conditions to the point of sustained hydrogen fusion. It may shine faintly from residual heat or limited fusion of heavier hydrogen varieties early on, but it does not enter the true main sequence. The dividing line is not merely brightness, it is whether core hydrogen burning becomes established as the star's long-term power source. On the other side of the sequence, a red giant may be far brighter and larger than many main sequence stars, yet it is no longer a main sequence object because its core hydrogen has been exhausted and its structure has shifted into a different regime. This helps clarify the category by contrast. Main sequence stars are not all stars of middling size, nor are they simply stars in general. They are stars in the long central phase where hydrogen fusion in the core determines the balance of the whole body. That is why the category includes so much apparent variety, but still excludes many objects that are undeniably stellar. The unity lies in the mechanism, the variation lies in the consequences of scale. Spectral classes, often labelled by the sequence of letters from the hottest stars to the coolest, describe some of those consequences. Massive blue stars occupy one end. Sun-like yellow stars sit nearer the middle. Small red dwarfs cluster toward the cool end. These categories describe temperature and spectral features, but when those stars are on the main sequence, the same deep rule still binds them together. One can think of the main sequence as the long stable answer to a basic stellar problem. How can a great ball of gas resist collapse under its own weight for immense spans of time? The answer is not the same in detail for every star, because details depend on mass, composition, and internal transport of energy, but the central answer remains consistent. A star fuses hydrogen in the core, releases energy, builds pressure, and holds itself in hydrostatic equilibrium. That is the common thread running through stars that otherwise differ so strongly in brightness and form that they might seem unrelated at first glance. The power of the concept is that it separates the essential from the incidental. A star may be brilliant or faint, cool or hot, large or small, but if its long-lived stability comes from core hydrogen fusion, it belongs to the main sequence. In that sense, the sequence is less a visual label than a statement about what the star is doing at the deepest level available to observation and theory. It tells where the energy comes from, why the structure endures, and why so many stars, despite their outward differences, can be understood as versions of the same basic phenomenon. The night sky encourages the eye to notice contrast. Some stars stand out as bright, some barely register, some shine white, some gold, some red. Astronomy goes further inward. It asks what process can generate these differences while still uniting so many stars under one name. The answer is as elegant as it is immense. Across the most common stars in the universe, a shared reaction in the core turns hydrogen into helium, and from that hidden transformation comes the broad band called the main sequence, where diversity in appearance rests on a deeper sameness of function. Gravity never stops acting on a star. Even after the long work of formation is over, even after hydrogen fusion has settled into the core and the star has taken its place on the main sequence, every layer of stellar gas is still being pulled inward by the mass beneath and around it. That fact gives a main sequence star its deepest problem and its deepest stability at the same time. A star is not a solid object resting on a surface. It is a self-gravitating sphere of hot plasma, with no rigid shell to hold it up, and no fixed framework to preserve its shape. If gravity were the only force in control, the whole structure would continue collapsing toward the centre. Yet a main sequence star does not simply keep shrinking. It holds itself in a durable state for immense spans of time. The reason is hydrostatic equilibrium, a condition in which the inward pull of gravity is balanced at every depth by an outward pressure gradient generated by the star's hot interior. This balance is not a minor detail of stellar structure. It is the condition that allows a star to remain a star in the steady sense. Without it, the main sequence would not exist as the dominant stage of stellar life. Hydrostatic equilibrium can sound abstract at first, but the idea becomes clearer when imagined layer by layer. Inside a star, material closer to the centre is under greater weight because it supports all the overlying gas above it. That weight compresses the inner regions, raising density and temperature. Hot matter pushes back. Pressure increases toward the centre for the same reason that compression becomes stronger there. At every depth, the inward force of gravity is met by a difference in pressure between one layer and the next. The deeper layer pushes outward more strongly than the layer above it pushes inward, and this pressure difference resists collapse. The result is not the cancellation of all motion or all activity. It is a persistent structural balance. Each shell inside the star is held in place by a contest between being pulled down by gravity and being supported from below by pressure. What makes this remarkable is that the balance extends through the whole body. A main sequence star is stable not because one single force overcomes another once and for all, but because this opposition is maintained continuously from the core outward. The shape that emerges from that balance is close to spherical, because gravity pulls matter inward toward the centre from all directions. When a fluid object is governed mainly by its own gravity, the most natural large-scale form is a sphere. Stars rotate, and some rotate rapidly enough to become slightly flattened. But the deeper principle remains. Their overall structure reflects the attempt of a hot fluid body to arrange itself under gravity, while internal pressure prevents further collapse. The familiar roundness of stars is therefore not cosmetic. It is physical evidence of equilibrium written into shape. Yet the equilibrium of a star is not like a stone resting on the ground. A stone is supported by contact with something beneath it. A star is supported by the conditions inside itself. Its pressure comes from hot particles in motion, from radiation moving outward, and in the densest cases from additional quantum effects that become important much later in stellar evolution. On the main sequence, the essential support comes from thermal pressure generated by the extraordinary heat of the interior and continually renewed by nuclear fusion in the core. That last point is what makes the balance sustainable. If a star were merely hot from formation and had no new source of energy, it would radiate that heat away and contract further. In a main sequence star, hydrogen fusion keeps feeding energy into the core, and that energy maintains the pressure needed to resist gravity over long intervals. This is why hydrostatic equilibrium and core fusion belong together. The equilibrium describes the balance of forces. Fusion provides the lasting energy source that makes the balance possible. In that sense, a main sequence star is a structure built from opposition but maintained by generation. It stays whole because the centre keeps producing the outward response that gravity demands. There is also a subtle, self-correcting quality built into this arrangement. A star on the main sequence is not perfectly frozen into a single unchanging state. Small shifts can occur. If the core begins to contract slightly, compression raises temperature. Higher temperature usually makes fusion proceed more rapidly. More fusion releases more energy, which increases pressure and resists further contraction. If the core expands a little too much, the opposite tendency appears. Temperature falls, fusion becomes less effective, and the reduced outward push allows gravity to tighten the structure again. This feedback helps stabilize the star. It does not mean stars are immune to change, but it does mean that the main sequence is a regulated phase rather than a fragile accident. A star can maintain equilibrium precisely because departures from it tend to trigger responses that move the structure back toward balance. That regulatory quality is one reason main sequence lifetimes can be so long. The star is not balanced once and abandoned. It is balanced continuously through the interaction of gravity, temperature, pressure, and fusion rate. The energy produced in the core must also travel outward, and this transport is part of equilibrium as well. In some stars, energy moves outward mainly by radiation, with photons being absorbed and re-emitted again and again through dense matter. In other regions, especially where conditions make radiative transport less efficient, hot material rises and cooler material sinks in convective motion, carrying energy physically from one level to another. The details vary with stellar mass and internal structure, but the principle remains the same. Energy generated deep inside cannot remain trapped forever. It moves outward through the star, helping sustain the temperature profile that pressure depends on. Hydrostatic equilibrium is therefore linked not only to fusion, but also to the way the star handles the energy fusion creates. A star is balanced because its interior is organized. The core generates energy. The surrounding layers transport it. Pressure at each depth answers the pull of gravity. The surface radiates energy into space. Every part is connected to every other part. That is why the structure can endure for so long without becoming simple. Stability in a star is not the absence of process. It is the successful coordination of many processes at once. The Sun offers a familiar example of this enduring balance. For billions of years it has remained on the main sequence, neither collapsing inward into a denser body nor expanding into a giant state. That stability has been sufficient for planets to orbit in steady paths, for climates to develop, and for life on at least one world to persist through immense spans of time. Yet even the Sun is not motionless. Waves move through it. Magnetic fields twist through its outer layers. Convection churns beneath the visible surface. Its light output varies slightly over activity cycles. Hydrostatic equilibrium does not erase all complexity. It operates underneath that complexity, holding the whole star in a coherent structure while surface and magnetic phenomena unfold above it. The same is true for other main sequence stars. Though their internal arrangements differ, low-mass red dwarfs can be deeply convective. More massive stars may have convective cores and radiative outer regions. The details change, the balance does not. What makes hydrostatic equilibrium especially powerful as a concept is that it explains both steadiness and limitation. A star can remain stable only as long as it has the means to maintain sufficient pressure against gravity. During the main sequence, that means sufficient hydrogen fusion in the core. Once the core hydrogen supply is exhausted, the old balance can no longer hold in the same way. The center begins to contract again. New stages of evolution are triggered, and the star leaves the main sequence. In this way, equilibrium is not eternal. It is the characteristic balance of a particular phase, supported by a particular source of energy. The star is stable because a specific nuclear process is active in a specific region of the interior. When that process changes, the equilibrium changes with it. This is why the main sequence is so long-lived but not permanent. It is stable on human, planetary, and often galactic timescales, yet still part of a larger life cycle shaped by fuel and gravity. The phrase hydrostatic equilibrium can therefore be read almost as a compact definition of main sequence existence. Gravity presses inward, pressure pushes outward. Fusion maintains the heat that pressure depends on. The star keeps its form because these conditions remain in active balance. From far away, the result looks deceptively simple, a steady point of light. From within the physics of the star, it is a continual resolution of opposing demands. Gravity insists on contraction, heat insists on expansion. The star persists because neither side fully wins. That tension gives the main sequence its long duration and its quiet dignity. Most stars in the universe spend the greater part of their existence in precisely this balanced state, neither newly forming nor near final collapse. but holding themselves together through an inward and outward contest renewed at every moment. The deeper question, then, is how such pressure is produced in the first place, and why only certain temperatures and densities allow the process of hydrogen fusion to sustain this balance at all. The star may appear stable from the outside, but its stability rests on conditions in the core so extreme that without them, gravity would resume the argument immediately. At roughly 10 million Kelvin in a stellar core, ordinary intuition about matter begins to fail. Hydrogen, which under calmer conditions consists of simple atoms with single electrons bound to single protons, can no longer remain in that familiar form. The heat is so intense that atoms are stripped apart into a plasma, a state in which electrons and nuclei move freely in a dense, charged sea. Yet temperature alone is not enough to explain what happens next. The deeper requirement is pressure, because hydrogen fusion does not begin merely when matter is hot, but when it is hot and compressed enough for nuclei to approach one another despite the electrical repulsion that naturally keeps positively charged protons apart. Every proton resists every other proton. In a cool gas, that resistance easily wins. In the core of a forming star, gravity keeps raising the stakes. It compresses the central layers, increases density, and drives temperature upward until the particles are moving with such speed and are packed so closely together that some collisions come near enough for the strong nuclear force to take over at extremely short range. That is the hidden threshold a protostar must cross before it can become a true main sequence star. The challenge is not simply producing heat. The challenge is forcing hydrogen into conditions where gravity can push matter into a regime that chemistry never reaches and ordinary matter never survives. Fusion begins only when the core becomes a place of relentless collision, deep pressure, and physical confinement on a scale that the outer star never reveals directly. This is why the birth of a main sequence star depends so strongly on what happens in the center. The visible surface may still be shrouded by gas and dust during the late protostellar stage. The outer layers may still be adjusting. But the defining transformation is buried far below, where gravity has turned a contracting cloud into an environment extreme enough to alter the rules of interaction between particles. In the core, hydrogen nuclei move rapidly because temperature reflects average particle energy. But even rapid motion does not automatically solve the problem of repulsion. Two protons approaching one another feel an electrical barrier, often called the Coulomb barrier, that tends to drive them apart before they can get close enough for the strong force to bind them. The strong force is far more powerful than the electrical force at very short distances, but it acts only across an extremely tiny range. Fusion therefore depends on particles reaching that range in the first place. In stars like the Sun, this happens partly because the distribution of particle energies is broad. Even if the average proton does not carry enough energy to overcome the barrier in a simple classical sense, some fraction of protons move faster than average. More subtly, quantum mechanics also allows tunneling, a process in which particles can pass through a barrier that would seem impassable in a purely classical picture. That small but crucial effect is one of the quiet reasons stars can shine at all. Without it, the temperatures required for hydrogen fusion would be far higher than they actually are, and many stars now filling the universe would never settle onto the main sequence. The physics is delicate in detail but immense in consequence. A star does not need every proton collision to succeed. It needs only enough successful fusions, sustained over time in an enormous core containing staggering quantities of matter, for the total energy release to become significant. In stars of roughly solar mass, hydrogen fusion proceeds mainly through the proton-to-proton chain, a sequence of reactions that begins when two protons come together. The immediate products are unstable, and the process involves intermediate steps, including the formation of deuterium and helium isotopes. before ordinary helium accumulates as an end product. What matters at the scale of stellar life is that hydrogen nuclei are gradually converted into helium nuclei, and in doing so a small portion of mass is released as energy. That energy does not emerge as flame in the terrestrial sense. It appears first in the form of energetic particles and radiation deep within the core, and from there it begins a long outward journey through the star. The amount of energy released per reaction is small in everyday terms, but the number of reactions occurring in a stellar core is so vast that the combined output becomes enough to oppose gravity across the whole body. In more massive main sequence stars, a different route called the carbon-nitrogen-oxygen cycle becomes increasingly important. There, heavier nuclei act as catalysts in a sequence that still converts hydrogen into helium, but does so more efficiently at higher temperatures. This distinction matters because it helps explain why massive stars respond so differently to gravity. Greater mass leads to stronger compression. Stronger compression leads to higher core temperatures. Higher temperatures make fusion more sensitive to small changes and far more intense overall. The star becomes brighter, hotter, and less patient with its fuel, even within the common identity of the main sequence. The details of fusion vary according to mass, and those details help shape the star's entire character. Pressure is the partner to temperature in all of this. Temperature measures the energy of particle motion, but pressure determines how tightly matter is packed and how often collisions occur. In a low-density environment, even very energetic particles might pass long intervals without meeting under useful conditions. In a stellar core, immense pressure ensures that the particles are crowded together. Gravity provides that pressure by the weight of the overlying layers. The deeper the core is buried under the mass of the star, the more intense the compression becomes. That is why stellar interiors cannot be understood by temperature alone. 1,000,000 degrees in a tenuous laboratory plasma is not the same as the dense heat of a stellar core. The frequency of interaction, the confinement of matter, and the total scale of the environment all matter. A protostar becomes a main sequence star only when gravity has compressed its center, enough for both temperature and density to rise into the regime where hydrogen fusion can support the structure. Before that point, contraction continues because the interior does not yet generate sufficient outward pressure. After that point, the core begins to answer gravity with an energy source that can endure for immense spans of time. There is a further subtlety here. Fusion in a star does not explode outward uncontrollably, because the conditions that permit it are also part of a self-regulating system. If the core compresses more strongly, temperature rises, and fusion tends to accelerate. The added energy output raises pressure and pushes back against further collapse. If the core expands too much, temperature falls, fusion slows, and the reduced outward support allows gravity to tighten the core again. This makes hydrogen burning in the main sequence a remarkably stable engine. It is intense beyond any familiar terrestrial comparison, but it is not chaotic in the way a bomb or sudden flare is chaotic. It is governed by the relation between pressure, temperature, and gravity inside a self-gravitating sphere. That relationship is what turns the violence of nuclear interaction into the steadiness of a star. The surface calm seen from a distance is therefore the visible expression of conditions in the core that are anything but gentle. Matter there exists in a state of continuous compression and collision. Energy is born in reactions that require quantum effects, extreme heat, and enormous pressure. Yet from that inner extremity comes the long-lived regularity of starlight. This is one of the quiet paradoxes at the center of stellar physics. Stability is powered by conditions that, if brought into human experience, would be utterly unendurable. The main sequence depends on the fact that the core is hot enough for hydrogen to fuse, dense enough for interactions to occur at a meaningful rate, and massive enough for gravity to maintain those conditions without immediately overshooting them into some different evolutionary path. Not every object formed from a collapsing cloud can do this. If the mass is too low, the core never reaches the required combination of heat and pressure, and the object remains below the threshold of true starlight. If the mass is high enough, fusion begins, and a new equilibrium becomes possible. The star is then no longer powered mainly by the memory of collapse. It is powered by ongoing nuclear transformation. Over time, helium ash accumulates in the core as hydrogen is used up, and the composition slowly changes. But during the main sequence, this central fact remains the same. The star lives by maintaining conditions under which hydrogen can continue to fuse. The threshold for that process, often described in simplified terms as a temperature of more than 10 million Kelvin, is not merely a number. It represents entry into a new physical regime, one in which pressure, density, quantum tunneling, and nuclear forces combine to create a durable source of energy inside a gravitating sphere of plasma. When that threshold is crossed, a star does not simply become hotter, it becomes structurally different. Gravity is still present, still compressing, still demanding inward motion. But now the core has an answer. Through fusion, mass becomes energy. Through energy, pressure is sustained. Through pressure, collapse is held in check. The great shining stability of the main sequence is therefore built upon a small and difficult victory won again and again in the center of every star two hydrogen nuclei coming close enough, under conditions harsh enough, for the universe to permit their union. A star does not need an enormous difference in material to become a very different kind of object. Add mass, and gravity deepens its hold on the interior. Remove mass, and that hold softens. From that single change, almost everything visible about a main sequence star begins to shift. Surface temperature, color, luminosity, radius, internal structure, fusion rate, and lifetime all follow, in one way or another, from how much matter has been gathered into the star. This is why mass is often treated as the master variable of stellar astronomy. It does not explain every detail by itself, but it sets the basic terms under which the rest of the star must operate. A main sequence star is always defined by hydrogen fusion in the core, yet the manner in which that fusion proceeds depends profoundly on the weight of the star pressing inward. The main sequence is therefore not a row of nearly identical lights. It is a spectrum of stellar solutions to the same underlying problem, each one shaped by how strongly gravity compresses the core. The contrast is so great that stars on different parts of the sequence can seem to belong to different categories of existence. At the low mass end are red dwarfs, small and cool, often faint enough to evade casual notice even when they are relatively nearby. At the high mass end are luminous blue stars, brilliant enough to dominate their surroundings, pouring out energy at a rate that makes the sun seem measured by comparison. Both remain on the main sequence while hydrogen fusion supports them, but the pace of their internal life is utterly different. The reason begins at the center. A more massive star has more material above each inner layer, and that greater weight produces stronger pressure in the core. Stronger pressure raises temperature. Higher temperature allows fusion to proceed much more rapidly. The result is not a modest increase in output, but a steep one. Luminosity rises far faster than mass alone would suggest. This is one of the most important and least intuitive features of main sequence stars. A star with several times the sun's mass can shine not several times more brightly, but tens or even hundreds of times more brightly, because fusion responds strongly to the harsher conditions gravity creates. In the most massive main sequence stars, the core is not merely hotter by degree. It is operating in a different regime of intensity, where the conversion of hydrogen into helium becomes extraordinarily rapid and the star's entire structure swells around that central power. At the lower mass end, the opposite tendency holds. A smaller star compresses its core less severely. Temperatures are lower by stellar standards. Fusion proceeds more slowly. Energy emerges at a gentler rate, and the star shines dimly compared with its larger counterparts. But what such a star lacks in brightness, it gains in endurance. Because it spends its hydrogen carefully, it can remain on the main sequence for extraordinarily long periods. This relation between mass and lifetime is one of the defining patterns of stellar evolution. More mass means more fuel in an absolute sense, but it also means a much faster burn rate. Less mass means less fuel, yet it is used so slowly that the total lifespan becomes vastly longer. A heavy star lives lavishly. A light star lives economically. The difference can stretch from a few million years at the upper end to tens or even hundreds of billions of years at the lower end. The main sequence contains both the most impatient stars and the most enduring ones, all because mass changes the conditions under which hydrogen fusion operates. Size follows from the same logic. A more massive star generally has a larger radius, though not in a simple one-to-one way. Greater energy generation in the core requires a larger structure through which that energy can move outward. The outer layers expand until the star reaches a new equilibrium between gravity and pressure. High-mass stars are therefore typically larger and more luminous, with hotter surfaces that shift their light toward white and blue. Low-mass stars remain smaller, cooler, and redder, with less radiant energy leaving the surface per unit time. The colour difference is not merely aesthetic, it reflects the physical condition of the surface, which in turn reflects the deeper structure of the interior. In this way, mass links what is hidden to what is seen. The invisible pressure in the core eventually declares itself as surface temperature, brightness, and spectral type. This is why astronomers can infer so much from starlight alone. The light carries the signature of conditions set by gravity far below the surface. Along the main sequence, stars are often described through spectral classes, ranging from the hottest blue stars through white and yellow stars down to orange and red ones. These classes organize what telescopes observe, but behind them lies the same physical ordering by mass and temperature. High-mass stars occupy the hot, bright upper part of the sequence. Intermediate stars like the Sun sit nearer the middle. Low-mass red dwarfs cluster at the cool, faint end. The line is continuous, but the change in character from one part to another is striking. A massive star tends to have a convective core and a radiative envelope. A very low-mass star may be convective through much of its whole structure. That difference matters because convection stirs material, redistributing heat and sometimes fuel. In the smallest main sequence stars, extensive convection allows hydrogen to be mixed more thoroughly through the interior, making their already slow fuel use even more effective over immense periods. In larger stars, fuel can be consumed more intensely in the core while the outer layers remain less involved. Once again, mass decides the broad pattern, and the broad pattern shapes how the star lives. The relationship between mass and brightness is especially revealing because it shows that a star's appearance is not a simple measure of how much matter it contains. Two stars may differ modestly in mass, and yet be separated by a much larger gulf in luminosity. This is why massive stars are so conspicuous even though they are much rarer than low-mass ones. They flood space with radiation. They can dominate young clusters and shape nearby gas clouds through intense ultraviolet light and stellar winds. Red dwarfs, by contrast, may vastly outnumber them while remaining visually modest. The universe is therefore not arranged so that the most common stars are also the easiest to notice. In many regions, The brightest stars command attention while representing only a small fraction of the stellar population. Mass creates that illusion by granting rare high-mass stars a disproportionate share of visible power. There is also a limit to how little or how much mass a main sequence star can have. Below a certain threshold, an object never compresses its core enough to sustain ordinary hydrogen fusion. Such a body becomes a brown dwarf rather than a true star, above the lower threshold. Main sequence life begins. At the upper extreme, stars can form with masses many times that of the Sun. Though the most massive are unstable in practice and lose material through strong radiation-driven winds. Even there, during the interval in which hydrogen fusion remains central, they still belong to the main sequence. The sequence therefore spans an enormous range, from the faintest true stars just above the fusion threshold to some of the brightest hydrogen-burning stars known. What unites them is the same core process. What separates them is how mass transforms the scale and consequences of that process. The Sun is useful partly because it sits in the middle of this spread. It is neither a giant blue star racing toward a short life, nor a red dwarf conserving its fuel over ages longer than the current cosmos has yet provided. Its mass places it in a moderate position, and from that moderation comes a lifetime of about 10 billion years on the main sequence. That makes it an instructive reference point. More massive stars will be hotter, brighter, and shorter lived than the Sun. Less massive stars will be cooler, dimmer, and longer lived. The Sun does not define the sequence, but it helps reveal the pattern by standing between its extremes. The deeper lesson is that the main sequence is not simply a list of stars doing the same thing in slightly different ways. It is a demonstration of how one variable can reshape an entire mode of existence. Mass decides how fiercely gravity squeezes the core. Core conditions decide how rapidly fusion proceeds. Fusion rate decides luminosity, temperature, size, and lifetime. All along the sequence, those consequences remain connected. The star becomes what its mass allows and demands. A little more matter can mean a much hotter surface. A little less can mean a lifespan extended beyond the age of galaxies as they are now observed. That is why the main sequence appears as an ordered structure rather than a random scatter. It records a law of stellar behavior, written across many kinds of stars at once. Seen this way, the sequence is not merely a classification tool, it is a visible translation of gravity's arithmetic. Matter is gathered, pressure rises, fusion answers, light emerges, and from the amount of mass present at the beginning, the rest of the star's long middle life is largely determined. What appears in the night sky as variety is, at a deeper level, the unfolding of one rule across many scales. Among main sequence stars, mass writes the script, and everything from colour to longevity becomes a consequence of how much weight the core must bear. At about 1 astronomical unit from the Sun, the star at the centre of the solar system can feel too familiar to serve as a scientific reference point. Its light structures the day, its gravity orders planetary motion, and its steady presence makes it easy to forget that it is a star among stars rather than a category apart. Yet in the study of the main sequence, that ordinary closeness is precisely what makes the Sun so useful. It is not the largest main sequence star, nor the smallest. It is not the hottest, the brightest, or the longest lived. It occupies a middle position, and because of that, it offers one of the clearest ways to understand what a main sequence star is, where neither the extremes of giant mass nor the slow patience of red dwarfs dominates the picture. The Sun is a hydrogen-burning star in stable hydrostatic equilibrium, and for that reason it belongs squarely within the most common stellar class in the universe. Its value lies in being typical enough to anchor comparison, but close enough to study in extraordinary detail. Through the Sun, the main sequence becomes less abstract. The principles that apply across the galaxy can be examined in one nearby star whose structure, activity, and long-term evolution can be traced with uncommon precision. In mass, the Sun sits near the middle of the known main sequence range. It is far above the threshold required for sustained hydrogen fusion, yet far below the masses reached by the brightest blue stars. That middle position shapes everything about it. Gravity compresses the solar core strongly enough to maintain the temperatures and pressures needed for fusion, but not so strongly that hydrogen is consumed at the frantic rate seen in high-mass stars. The result is moderation in the deepest stellar sense. The Sun is luminous on human terms, but not extreme on cosmic terms. Its surface temperature places it among yellow-white stars rather than the hottest blue stars or the coolest red ones. Its radius is large enough to dominate the inner solar system visually, yet modest beside the swollen scale of more massive stars. Most importantly, its rate of fuel consumption gives it a main sequence lifetime of roughly 10 billion years, a span long enough to support the slow development of planetary systems and biological complexity, but not so long that the future of the star disappears into timescales wholly detached from the present universe. This makes the Sun a kind of middle case not only in mass, but in tempo. It lives neither too quickly nor too slowly. The Sun has already spent nearly half of that main sequence lifetime in its present state. It formed about 4.5 billion years ago from a collapsing molecular cloud, passed through its protostellar youth, and entered the main sequence once hydrogen fusion in the core became established. Since then, it has remained in the long stable middle of stellar life, generating energy through the proton-to-proton chain and balancing inward gravity with outward pressure from its hot interior. That continuity matters because it reveals what the phrase stable star truly means. The Sun is not unchanging, but its changes on human timescales are subtle enough that the star appears constant while the deeper evolutionary clock advances slowly underneath. Day after day, the Sun radiates energy outward. Year after year, planetary orbits remain governed by nearly the same central mass. Over geological time, however, the slow conversion of hydrogen into helium changes the core composition and gradually alters the star's output. Even during the main sequence, a star is not perfectly static. It evolves with instability. The Sun demonstrates the balance well. It remains reliably solar while slowly becoming brighter over billions of years as helium accumulates in the core and the internal structure adjusts. That quiet increase is part of main sequence life itself. It shows that stability does not mean absence of development. It means development unfolding within a durable equilibrium rather than through rapid structural upheaval. This is one reason the Sun serves so well as a reference point. It reveals the main sequence as a long-controlled process rather than a frozen state. The solar interior also provides a model for how an ordinary main sequence star is organized. At the center lies the core, where temperatures reach many millions of degrees, and hydrogen fusion releases the energy that powers the whole star. Outside the core is a radiative zone, where energy moves outward largely through repeated absorption and re-emission of photons. Beyond that lies the convective zone, where hot plasma rises and cooler material sinks, carrying energy through bulk motion. At the visible surface, called the photosphere, that long interior journey emerges as sunlight. Above the photosphere lie the chromosphere and corona, outer layers shaped by magnetic activity and heated to surprising temperatures. This structure matters not because the Sun is unusual, but because it is accessible. Solar physics allows the inner logic of main sequence life to be studied with great richness. Oscillations rippling through the Sun reveal information about the interior. Solar neutrinos carry evidence of fusion in the core, magnetic fields, sunspots, prominences, and flares show that even a middle-aged main sequence star can be dynamically active at the surface while remaining stable in overall structure. The Sun is therefore ordinary in its category, but not simple in its behaviour. That combination makes it especially instructive. It reminds astronomy that a typical main sequence star is not a featureless light source. It is layered, active, self-regulating sphere whose steady existence depends on conditions buried far below the surface. The Sun also helps place stellar lifetimes into a form that can be compared meaningfully with other stars. A main sequence lifetime of about 10 billion years sits between very different regimes. A star several times more massive than the Sun will burn hotter and brighter, but its lifetime will shrink sharply because the extra gravity raises core temperatures and accelerates fusion. Such a star may remain on the main sequence only for millions or tens of millions of years. By contrast, a red dwarf with much lower mass may consume its hydrogen so slowly that it can remain on the main sequence for tens or even hundreds of billions of years. Against that full scale, the Sun becomes a useful benchmark. It is neither brief enough to be called impatient nor slow enough to seem almost timeless. Its lifetime is long relative to planets and civilizations, yet short relative to the possible endurance of the smallest stars. This middle timescale has profound consequences. It allows a planetary system like the solar system to remain under a relatively stable energy source for billions of years, which in turn allows atmospheres, oceans, climates, and biological evolution to unfold gradually. The Sun's position on the main sequence is therefore not merely an astronomical fact. It is one of the conditions that made Earth's history possible. That does not mean solar normality guarantees habitability everywhere, but it does show how the character of a main sequence star can shape the long environmental story of the worlds around it. There is another reason the Sun matters as a standard. Because it is so well observed, many stellar properties elsewhere are expressed in solar terms. Masses are compared to the mass of the Sun, radii are measured against the solar radius, luminosities are scaled to solar luminosity. This practice is not only convenient, it reflects how central the Sun is to the language of stellar comparison. The solar system provides a familiar anchor from which the wider diversity of stars can be described. A star half as massive as the Sun, 10 times as luminous as the Sun, or many times larger in radius than the Sun can be located conceptually because the Sun offers a known middle case. It functions almost like a unit of ordinary starlight. Yet the Sun must be handled carefully in thought, because familiarity can also mislead. It is easy to assume that what is ordinary for the Sun is ordinary for stars in general. In one sense, that is true. The Sun is a genuine main sequence star, and the principles of core fusion, hydrostatic equilibrium, and mass-governed evolution all apply to it clearly. In another sense, however, the galaxy is filled in greatest number not with stars like the Sun, but with smaller and dimmer red dwarfs. The Sun is intermediate, not average in every possible statistical way. Its importance comes from balance and accessibility, not from being the single most common stellar type. That distinction matters because it keeps the Sun from becoming a false template for the entire main sequence. It is best understood as a central example, not a universal pattern. As the Sun continues through its present stage, it will keep converting hydrogen into helium in the core for several billion years more. Eventually the core hydrogen supply will become depleted enough that the present form of equilibrium can no longer continue unchanged. The core will contract, the outer layers will expand, and the Sun will leave the main sequence for a red giant future. That later transformation is essential to stellar evolution, but it also clarifies what the main sequence really is. It is the long era during which a star's core hydrogen burning governs its structure. The Sun is in that era now, and because it stands near the middle of the main sequence in mass, brightness, and lifetime. It provides an especially clear expression of what such a life looks like. It is a star neither rushed nor nearly eternal, neither dim to the point of obscurity nor brilliant to the point of violence. It is a sustained nuclear equilibrium, shining steadily through a vast but finite span. In that measured endurance, the sun becomes more than the local source of daylight. It becomes a guide to the broader stellar order, showing how an ordinary main sequence star can hold itself together for billions of years while slowly transforming the conditions of the worlds that depend on its light. A star 10 times the mass of the sun does not live 10 times as long. It lives far less. This is one of the most revealing asymmetries in the main sequence, and one of the clearest signs that stellar life is governed not by fuel alone, but by the rate at which that fuel is consumed. Massive stars begin with a great advantage in raw material. They gather more hydrogen, build larger bodies, and compress their interiors under far stronger gravity than stars like the Sun ever experience. Yet that very strength becomes the reason their lives move so quickly. The deeper weight of the overlying layers drives the core to much higher temperatures and pressures, and once those conditions are established, hydrogen fusion no longer proceeds with measured restraint. It accelerates. The star becomes not merely larger than the Sun, but vastly more luminous, radiating energy into space at a pace that transforms abundance into rapid expenditure. The paradox of massive main sequence stars is that their greater reserves do not buy them patience. They force them into extravagance. What looks like abundance at the beginning becomes urgency at the center. The engine of a massive star is not simply a scaled-up version of the solar core. It operates in a more intense regime. In stars around the Sun's mass, hydrogen fusion proceeds mainly through the proton-to-proton chain, which is effective at the temperatures found in moderate stellar interiors. In much more massive stars, higher core temperatures make the carbon-nitrogen-oxygen cycle increasingly dominant. This process still turns hydrogen into helium, but it does so in a way that is far more sensitive to temperature. A modest rise in core temperature can produce a dramatic rise in energy generation. That sensitivity matters because it helps explain why massive stars are so bright. Their stronger gravity raises core temperatures, and the fusion process responds with a steep increase in output. The star then has to adjust its entire structure to carry that energy outward. Its radius expands, its surface temperature rises, and its luminosity climbs to levels that can exceed the Sun's by hundreds, thousands, or in extreme cases far more. The result is a star that may appear to dominate its region of space, even while representing only a brief and uncommon phase of stellar existence. Massive stars are therefore among the brightest objects in stellar astronomy, but also among the least enduring. Their brilliance is not a sign of efficiency, it is a sign of rapid consumption. The common intuition that more fuel means longer survival fails because the rate of burning rises much faster than the amount of fuel available. A star with several times the Sun's mass does not merely have a somewhat hotter core. It has an interior compressed into such demanding state that hydrogen is processed at a remarkable pace. The extra fuel is real, but the demand placed upon it is greater still. This is why a star of about 10 solar masses may remain on the main sequence for only around tens of millions of years, while the Sun can remain there for about 10 billion. The massive star begins with more matter, and yet reaches the end of its core hydrogen-burning life vastly sooner. In cosmic terms, that is a hurried existence. It means that some of the brightest stars in a young cluster may already be nearing the end of their main sequence lives, while smaller stars around them are still only at the beginning of long, stable careers. Stellar populations therefore contain a quiet hierarchy of mortality. The stars that shine most intensely are often the first to leave the stage. This haste affects the structure of massive stars in ways that go beyond brightness alone. Their interiors are organized differently from those of smaller stars. Many have large convective cores, where hot material rises and cooler material sinks, stirring the central regions and helping distribute hydrogen through the zone where fusion is most active. Outside the core, the outer layers may transport energy mainly through radiation. The details vary with mass, composition, and rotation, but the general pattern is one of internal power concentrated at great intensity. The star is not lazily using one part of itself while leaving the rest unchanged. It is under constant structural pressure to move immense energy outward, while gravity keeps the whole body compressed. That tension contributes to powerful stellar winds in the most massive stars, where radiation pushing on the outer layers can drive material away into space. In those cases, the star may lose a significant amount of mass even while still on the main sequence. This is another way in which excess becomes cost. The luminosity that makes the star spectacular also helps strip material from it, shaping its later evolution long before core hydrogen is fully exhausted. Massive stars therefore live under conditions that are not only bright, but erosive. They spend themselves from both within and without. Their appearance reflects that intensity. Surface temperatures are much higher than those of the Sun, often shifting their light strongly toward the blue and ultraviolet. To surrounding space, this matters enormously. Ultraviolet radiation from massive stars can ionize nearby gas clouds, carving glowing regions out of star-forming nebulae and altering the conditions under which later stars and planets might form. In this way, the short main sequence lives of giants have effects that extend well beyond their own interiors. A small number of such stars can dominate the visible character of a young stellar region. They can light, sculpt, heat, and disturb the surrounding medium, even though they are vastly outnumbered by faint red dwarfs. This makes them astrophysically influential despite their rarity. A galaxy may contain countless low-mass stars living quietly for immense spans, yet a handful of high-mass stars can command disproportionate attention because of the radiation and winds they release during their brief lives. Their importance is therefore ecological as much as individual. They reshape the environments in which future stellar generations emerge, but the central drama of their main sequence existence remains the same. The core burns too well to last long. There is something almost counterintuitive in the fact that greater gravitational power leads not to greater permanence, but to greater vulnerability to time. In a massive star, gravity drives the interior into conditions so extreme that the solution to collapse becomes costly. Fusion pushes back successfully, but only by consuming hydrogen at a rate that rapidly transforms the core's composition. Helium ash accumulates. The fraction of available central hydrogen declines. The star remains stable while this process continues. But the stability is expensive. It is bought with speed. This is why the main sequence is not one uniform plateau of calm. It contains stars living at profoundly different tempos. The Sun, in its moderate balance, evolves slowly enough that life and geology can unfold around it over billions of years. A high-mass star lives in another register entirely. Its childhood is brief, its maturity compressed, its future arrives early, on a planetary timescale. Such a star would be a difficult center around which long biological histories might develop, not only because of its short lifespan, but because of the harsh radiation environment it creates. The very qualities that make massive stars visually magnificent also make them unstable foundations for prolonged planetary calm. That does not make them less important. It makes them important in another way. They are engines of rapid change. The end of the main sequence comes quickly for these stars because core hydrogen exhaustion is reached so soon. Once the central hydrogen supply falls too low to support the existing balance, the core begins to contract and the star moves into later stages of evolution. For a massive star, those later stages unfold with a sequence and violence that smaller stars do not experience in the same way. Heavier elements can begin to fuse in succession, each for a shorter interval than the last, until the star approaches collapse and explosive death. But even before those final events, the fast life of the giant has already carried major consequences. Massive main sequence stars manufacture helium rapidly, enrich their surroundings through winds, and prepare the conditions for later supernovae that will scatter heavier elements into the galaxy. In that sense, their brief lives are not marginal episodes. They are central to cosmic history. Many of the elements later incorporated into planets, atmospheres, and living systems depend on stars that lived quickly and ended violently. The main sequence giant is therefore both a short-lived star and a long-term influence. Its personal duration is small, its legacy is large. What makes this especially striking is that the process begins from the same basic principle that defines all main sequence stars. Like every star in this category, the giant is converting hydrogen into helium in the core and maintaining hydrostatic equilibrium through the outward pressure created by fusion. The difference is one of scale and consequence. Mass pushes the core into a hotter regime. The hotter regime intensifies fusion. Intensified fusion creates immense luminosity. Immense luminosity shortens the star's stable life. The chain is consistent from beginning to end. Nothing about the fast life of a giant is accidental. It is the direct outcome of the same physics that governs all main sequence stars, driven to a more extreme conclusion. This is why the upper part of the main sequence feels so dramatic, even when described quietly. There is no need to exaggerate it. The facts already carry the shape of the story. The brightest hydrogen-burning stars are not the most secure, they are the most extravagant. They answer gravity with overwhelming power, and in doing so they consume the conditions of their own stability. Their brilliance is real, but it is purchased with time. Against the immense background of the universe, they are like brief intensifications in a longer field of starlight, burning through their fuel with such force that even their abundance at birth cannot protect them from a rapid end. More matter gives them more to spend. It does not teach them how to spend slowly. Near the cool red end of the main sequence, the scale of stellar life changes so dramatically that the usual language of long duration begins to feel inadequate. A red dwarf is smaller than the Sun, fainter than the Sun, and far less conspicuous in the sky than the more luminous stars that often define human ideas of starlight. Yet in terms of endurance, these modest stars surpass almost everything else on the main sequence. Their significance does not come from brilliance, but from restraint. Gravity compresses them less severely than it compresses stars like the Sun, and because the core is not driven to such extreme temperatures, hydrogen fusion proceeds at a much slower rate. The star produces less energy, glows more dimly, and spends its fuel with extraordinary care. What seems at first like a limitation becomes a profound advantage in time. A red dwarf may burn for tens of billions or even hundreds of billions of years, far longer than the current age of the universe. In that sense, these are not merely long-lived stars. They are stars whose full life stories have not yet had time to unfold anywhere in the cosmos. The universe is still too young to show their endings. This gives red dwarfs a special place in the story of the main sequence. They are not only common, they are the most patient fires the universe has yet made in abundance. Their patience begins, as always, with mass. A red dwarf contains less material than the Sun, often far less. But the more important fact is that this smaller amount of matter creates weaker gravitational pressure in the interior. The core still becomes hot enough for hydrogen fusion. Otherwise, the object would never qualify as a true star. But it does so just above the threshold required for sustained burning rather than far beyond it. The result is a quieter internal regime. Fusion occurs, but at a slow pace. The star radiates energy modestly. Its surface temperature remains low by stellar standards, which is why it appears red rather than yellow, white, or blue in the visible sky. Such stars are often too faint to draw much attention. Many of the nearest stars to the Sun are red dwarfs, yet none dominate the night in the way brighter, but more distant stars do. This is one of the quiet illusions created by the sky. The most common stars are often the least obvious to unaided sight. Their importance emerges not through spectacle, but through number and duration. Red dwarfs fill the galaxy in immense quantities. They are the background population of stellar life, numerous and persistent, forming the long-lived majority beneath the brighter but rarer stars that more easily capture notice. What makes red dwarfs especially remarkable is not only that they burn slowly, but that many of them are structured in a way that helps them use their fuel with unusual thoroughness. In a star like the Sun, hydrogen fusion occurs in the core, and the helium produced gradually accumulates there. Much of the outer hydrogen is not mixed deeply enough into the center to be used during the star's main sequence life. Over billions of years, the core changes composition, while the outer layers remain comparatively less involved in the central burning process. In many red dwarfs, especially the smaller ones, convection extends through much or even all of the star. Hot material rises, cooler material sinks, and the interior is stirred over long periods. This means hydrogen from outer regions can be brought inward, and helium can be redistributed more broadly. The star is not limited to using only a relatively isolated core fraction of its hydrogen supply. It can, in effect, access a much larger share of its fuel over time. This deep convective mixing is one reason red dwarfs can remain on the main sequence for such astonishing spans. They are not only slow burning, they are efficient in a structural sense, able to make use of more of what they contain. Their modest gravity, low luminosity, and extensive mixing combine into one of the most economical stellar lifestyles known. This is why estimates for red dwarf lifetimes become so immense. A star with about half the Sun's mass may remain on the main sequence for many tens of billions of years. Smaller examples may continue far beyond that, reaching durations that approach or exceed 100 billion years. These numbers matter not as exaggerations, but as direct consequences of stellar physics. The universe itself is about 13.8 billion years old, which means no red dwarf has yet had time to exhaust its core hydrogen and pass through the full later evolution that more massive stars have already completed many times over. There are white dwarfs from sun-like stars, there are neutron stars and black holes from massive stars, but there are no dead red dwarfs produced by ordinary age, because the cosmos has not been around long enough for them to die that way. This places red dwarfs in a strange position. They are among the oldest stars now shining, yet the class as a whole is still in the early part of its possible history. Their future stretches beyond the present age of galaxies in forms that astronomy can model, but not yet observe directly in full. In that sense, red dwarfs are both ordinary and temporally mysterious. They are familiar objects whose ultimate fate remains a matter of theory, because time itself has not carried the universe far enough. Their stability has led astronomers to consider them carefully in discussions of planetary habitability. A long-lived star offers something profoundly valuable to any world orbiting it: time. Time for planets to cool, for atmospheres to settle, for chemistry to grow more complex, and perhaps for life to emerge and evolve. Compared with stars that burn out in a few million or few billion years, a red dwarf appears to offer an almost extravagant extension of opportunity. A planet in stable conditions around such a star could, in principle, experience environmental continuity over spans much greater than the time Earth has had around the Sun. This possibility has made red dwarfs central to the search for exoplanets and to reflections on where life might endure longest in the universe. Yet the picture is not simple. The same stars that live so long can also be magnetically active, especially in youth, producing flares and bursts of radiation that may complicate the habitability of close-orbiting worlds. Because red dwarfs are faint, their habitable zones lie close to the star, which can expose planets to tidal locking and to stronger influence from stellar activity. So the promise of duration comes with constraints. Still, what keeps red dwarfs important is not the claim that they are ideal in every case, but the fact that they offer something no short-lived star can offer: a stable main sequence platform extending across immense tracts of cosmic time. Even where habitability is uncertain, the stars themselves remain extraordinary examples of long-term equilibrium. There is also a broader cosmic implication in their abundance and longevity. As the universe ages, the bright blue giants disappear quickly. Sun-like stars eventually leave the main sequence. Over very long times, red dwarfs increasingly come to dominate the surviving stellar population, not because they were ever the brightest, but because they outlast so many others. Their role in the far future of galaxies may therefore be even more central than their role now. The present universe still contains many kinds of stars in different phases, but deep into cosmic time, the patient red dwarfs will remain when many other lights have faded or transformed. They are, in a sense, the long memory of stellar formation. Once born, they remain. This makes their modest appearance almost deceptive. A red dwarf does not announce its significance through intensity. It keeps its significance by persisting. The contrast with massive stars could hardly be sharper. A giant blue star floods space with radiation and dies young. A red dwarf emits sparingly and endures. One dominates by brilliance, the other by duration. Both are main sequence stars. Both are powered by hydrogen fusion, and both are held together by hydrostatic equilibrium. Yet their lives differ so profoundly that they seem to reveal opposite philosophies of stellar existence. The red dwarf is the patient answer to gravity, the slow conversion of hydrogen into time. It shines less fiercely because it has no need to do more than is required to remain stable. Its core conditions are enough for fusion, but not so extreme that fusion rushes forward wastefully. In that measured pace lies the reason these stars matter so much. They are not simply survivors by chance. Their entire structure is arranged toward endurance. In a universe where many dramatic objects owe their fascination to rarity or violence, the red dwarf offers another kind of significance. It is common, quiet, and durable. It embodies the idea that the most important processes in the cosmos are not always the most luminous. Sometimes they are the slowest. Sometimes the stars that matter most for the long future are those that conserve their energy, remain structurally simple, and keep burning long after brighter neighbours have passed into memory. The main sequence contains many ways of being a star, but none stretch time more patiently than this. A red dwarf does not race through its hydrogen, it inhabits it, and because of that, the smallest stars may become the longest-lasting lights the universe will ever know. Around a main sequence star, habitability begins not with life, but with duration. A planet may have the right ingredients in some raw sense, with rock, water, carbon-bearing chemistry, and a source of energy. Yet none of those conditions matter for long if the central star changes too violently or too quickly. The main sequence is important to habitability because it is the long, stable era of stellar life. The phase in which a star's energy output is governed by steady hydrogen fusion in the core rather than by the instability of youth or the upheaval of old age. That stability does not guarantee that any given planet will become living or even remain temperate. Planetary atmospheres can be lost. Surfaces can freeze or overheat. Magnetic shielding can fail. Impacts can reshape climate, and internal geology can either support or undermine long-term environmental balance. But without a sufficiently steady star, many of those slower planetary stories never have enough time to matter. Main sequence stars are therefore not interesting to habitability because they are automatically gentle. They are interesting because they provide the long middle interval in which worlds have a chance to become more than newly formed objects. A star on the main sequence offers continuity, and continuity is one of the rarest resources in cosmic evolution. The clearest example is the Sun. Earth has not existed around a star in rapid transition. It has orbited a main sequence star that, despite magnetic cycles and gradual long-term brightening, has remained structurally stable over billions of years. That has allowed oceans to persist, climates to fluctuate without permanent collapse into one state or another, and biology to move through an immense sequence of transformations. The Sun has not been perfectly constant. No star is. Even during the main sequence, luminosity changes gradually as hydrogen is converted into helium in the core. The young Sun was dimmer than it is now, and the future Sun will continue to brighten slowly as the internal structure adjusts to a growing helium fraction at the centre. Yet that gradualness is precisely the point. Change has occurred, but at a pace that planetary systems can respond to through atmosphere, chemistry, and geology. Habitability does not require absolute stillness from a star. It requires that stellar change be slow enough for a world to remain within viable bounds over the timescales needed for complexity to emerge. A main sequence star provides that kind of pacing more reliably than stars in more unstable stages. Mass, however, changes the picture profoundly. The same property that governs a star's brightness and lifetime also governs how promising it may be as a long-term home for habitable worlds. Massive main sequence stars live too quickly. They burn through core hydrogen at such a rapid pace that their stable lifetimes can shrink to a few million or tens of millions of years. That is an immense interval by human standards, but it may be too short for the slow environmental and chemical developments that lead to complex biospheres. In addition, massive stars emit intense ultraviolet radiation and produce energetic stellar winds that can make nearby environments harsh. A planet receiving moderate surface temperatures around such a star might still face a difficult radiative setting, and the star's eventual evolution toward instability arrives too soon. These stars are spectacular sources of light, but poor candidates for prolonged planetary calm. Their main sequence phase is real, yet the timescale of that phase is compressed enough that habitability becomes much harder to imagine as an enduring condition. At the other end of the sequence, red dwarfs offer the opposite advantage. Their lifetimes are so long that they can remain stable hydrogen-burning stars for tens or hundreds of billions of years. From the standpoint of duration alone, they appear almost ideal. A world around such a star could in principle have far more time than Earth has had to sustain oceans, climate cycles, and biological experimentation. This is one reason red dwarfs have become so central to exoplanet research. They are common, nearby, and long-lived, and because they are faint, planets orbiting in temperate zones pass close to the star, making them easier to detect through transit and radial velocity methods. Yet the same closeness introduces complications. A habitable zone around a dim red dwarf lies much nearer the star than Earth lies from the Sun. At those distances, planets can become tidally locked, turning one hemisphere permanently toward the star and the other away. That does not automatically destroy habitability, since atmospheres and oceans may redistribute heat, but it changes the planetary regime significantly. Red dwarfs can also be magnetically active, especially during long youthful phases, producing flares and radiation bursts capable of eroding atmospheres or stressing surface conditions. So the habitability of red dwarf systems remains a problem of trade-offs. They offer time in abundance, but often under closer and more demanding stellar influence. Somewhere between these extremes lie stars more modest than the most massive giants, and more luminous than the faintest red dwarfs. These intermediate stars, including sun-like stars and somewhat smaller orange dwarfs, are often treated as especially interesting because they balance duration and environmental gentleness in a way that seems promising. A star somewhat less massive than the Sun may remain on the main sequence longer while emitting less intense high-energy radiation than more massive stars. Its habitable zone lies closer in than Earth's orbit around the Sun, but not so close as in the most compact red dwarf systems. Such stars may offer long, stable intervals without some of the most severe trade-offs found at either extreme of the main sequence. This does not make them perfect. Habitability remains a planetary outcome shaped by atmosphere, composition, orbital history, impact record, magnetic shielding, and geological cycling. Still, the character of the star sets the boundary conditions under which those planetary variables must operate. The star supplies the long-term energy flow, and the regularity of that flow matters. What is often called the habitable zone is a useful first approximation but not a final answer. It refers to the range of distances from a star where a planet with suitable atmospheric conditions could maintain liquid water at the surface. This concept is central because liquid water is one of the most plausible solvents for life as it is currently understood. But the habitable zone is not fixed once and for all. It depends on the luminosity of the star, and because main sequence stars change slowly over time, the habitable zone also moves. In the solar system, the Sun's gradual brightening has meant that the zone favourable for surface liquid water has shifted outward over billions of years. Earth has remained inside a broadly habitable band because planetary feedbacks and the pace of solar evolution have together permitted long continuity. Around other stars, the same principle applies. A star that evolves too quickly or varies too violently may shift its habitable zone in ways that narrow the window for stable surface conditions. A star that evolves more slowly offers a longer interval during which planets may remain within favourable limits. Thus, the importance of the main sequence to habitability lies not only in the existence of a habitable zone, but in the persistence of that zone over geological time. Main sequence stability also matters because planets themselves are slow to mature. Young worlds endure bombardment, volatile loss, tectonic settling, crust formation, ocean development, and atmospheric evolution. Even if life begins relatively early, the rise of complex ecosystems may require immense spans of continuity. On Earth, single-celled life appears relatively early in the planet's history, but multicellular complexity and technological intelligence arrive much later. This may be one path among many, but it underscores the same lesson: time matters. A star whose stable lifetime is brief does not merely reduce the opportunity for life to appear, it compresses every later stage as well. By contrast, a star that remains on the main sequence for billions or tens of billions of years provides repeated opportunities for recovery after catastrophes, for atmospheric repair, and for long evolutionary experiments. The main sequence is therefore not just the phase in which planets receive light. It is the phase in which worlds receive enough consistent time for consequences to accumulate. Even so, stellar stability alone is never enough. Venus and Earth orbit the same star and tell very different stories. Mars, farther out, preserves evidence of a past that may once have been wetter and more active. Yet it did not remain Earth-like. The difference lies in planetary mass, atmospheric evolution, internal heat, magnetic shielding, and many other variables. This is an important corrective to any simple reading of the main sequence. A good star does not make a good world by itself. It creates the possibility space within which planetary histories unfold. Habitability is an interaction, not a gift. The star sets the energy budget and the timescale. The planet determines how that budget is used, stored, reflected, amplified, or lost. That is why the search for habitable worlds has become a search for systems, not only stars. Astronomers ask what kind of star is present, how old it is, how active it is, where the planets orbit, whether those planets are rocky, whether atmospheres can be detected, and whether the long-term stellar environment supports stability rather than repeated disruption. In that broader view, the main sequence takes on a special importance. It is the era in which stars are most likely to support environmental continuity without either the violence of formation or the instability of post-main sequence expansion. It is the great middle interval in which the possibility of habitable worlds can be meaningfully assessed. Across the galaxy, countless planets orbit main sequence stars of many kinds. Most will never host life. Some may host only simple chemistry. A smaller number may achieve something more enduring. What keeps the question open is the same fact that defines the stars themselves. The main sequence is long. It gives worlds time to cool, to change, to fail, to recover, and perhaps to become inhabited. In the search for life beyond Earth, that length may be the most generous condition a star can offer. The main sequence does not promise living planets. It makes them possible by refusing to end too soon. In a spiral galaxy viewed from afar, the visible structure seems almost architectural. A bright central bulge thickens toward the middle. Curving arms unwind into the dark beyond. Dust lanes cut across the light in irregular bands. Star clusters gather like denser knots along the disk. Yet beneath that grand pattern lies a simpler truth about what is doing most of the shining. The luminous story of a galaxy is written primarily by stars in their long stable phase, stars that are neither newly forming nor already transformed into their final remnants, but are spending the central stretch of their lives on the main sequence. This matters because the main sequence is not merely one chapter in stellar evolution. It is the chapter where most stars spend most of their time, and therefore the chapter that fills the universe most persistently with starlight. A galaxy contains nebulae, white dwarfs, neutron stars, black holes, giants, supergiants, and clouds of cold gas waiting to collapse. All of these are real parts of its structure, but the ordinary enduring light that defines a galaxy over long intervals comes mainly from stars that are quietly converting hydrogen into helium in their cores. The main sequence is not the dramatic edge of stellar life. It is the great middle field, and because it is both populous and long-lived, it dominates the visible population of stars across cosmic space. That dominance begins with formation. Stars are born from molecular clouds made mostly of hydrogen, and the threshold for becoming a true star is the onset of sustained hydrogen fusion in the core. Once that threshold is crossed, the object enters the main sequence, and in many cases it remains there for the overwhelming majority of its existence. A massive star may live quickly, but even then its main sequence phase is still the defining portion of its active luminous life before later instability sets in. A low-mass star may remain on the main sequence for spans so immense that no later phase has yet occurred anywhere in the current universe. This means the main sequence is not just common because many stars reach it. It is common because stars stay there. When a category contains objects that are both numerous and long-lasting, that category will naturally dominate the census at almost any given moment. Astronomy sees this clearly in the Milky Way. Most stars in the galaxy are main sequence stars, especially the low-mass red dwarfs that fill the stellar background in immense numbers. They're often too faint to command attention individually, but together they make up the deep reservoir of stellar existence. Above them in brightness are stars like the Sun, less numerous but still abundant, and above them the rarer luminous stars that, while short-lived, are also in their hydrogen-burning phase for the interval in which they are most visibly stellar. Across this full range, the main sequence occupies the centre of the stellar population. There is an important distinction, however, between what is most common and what is most easily noticed. The brightest stars in a galaxy are not the most numerous. They're often massive main sequence stars or evolved giants that stand out because luminosity travels well across distance. A red dwarf may be vastly more common than a hot blue star, and yet be far harder to see from afar. This means that the visible appearance of a galaxy is shaped by two overlapping truths. In terms of sheer number, the galaxy is dominated by faint low-mass main sequence stars. In terms of the most conspicuous light, the upper end of the main sequence contributes disproportionately because luminous stars can illuminate surrounding gas, define the appearance of young stellar populations, and remain visible across great distances. Even here, though, the main sequence remains central. Whether through countless dim red dwarfs or through brilliant but rarer blue stars, hydrogen-burning stars provide much of the light by which galaxies are recognized. The visible universe is therefore filled not mainly with exotic stellar exceptions, but with stars in their long middle condition. Their importance lies partly in spectacle at the bright end, but even more in persistence at the faint end. This becomes even clearer when stellar evolution is considered as a matter of time. A galaxy is not frozen. Stars are born, age, and die. Gas is recycled. Heavy elements accumulate. Star formation rises in some regions and fades in others. Yet through all of this, the main sequence remains the most stable component of the stellar population. Short-lived phases pass quickly. Protostellar youth is brief. Giant phases are comparatively short. Remnants such as white dwarfs and neutron stars endure, but they do not generate starlight through the same ongoing nuclear process and often contribute less to the broad visible glow of a galaxy than the stars that are still burning hydrogen. The main sequence sits at the centre of this changing system as the long interval where a star remains structurally coherent and steadily luminous. Because stellar populations are continually being sampled at random points in their histories, the stages that last longest are the stages most likely to be present in large numbers. This is why the main sequence is not merely a theoretical line on a diagram, but the dominant lived condition of stars in the universe as it is now observed. On cosmic scales, that fact gives the main sequence a deeper significance. Galaxies are among the most recognizable structures in the universe, not because every part of them shines equally, but because their stars do. The light that reaches telescopes from nearby galaxies and from systems so distant that their photons began traveling long before Earth formed is largely the cumulative output of stellar populations dominated in number by main sequence stars. Even when unresolved into individual points, that light carries the signature of the stars producing it. Blue galaxies rich in recent star formation contain many hot, luminous young main sequence stars, which shift the integrated light toward shorter wavelengths, redder. Older galaxies may be dominated in visible character by cooler stars and aging populations. Yet beneath those differences, the long hydrogen-burning history of stellar populations still shapes the spectrum, mass distribution, and chemical story of the system. Main sequence stars are therefore not only individual lights, they are statistical builders of galactic appearance. They are also the engines through which much of cosmic chemistry proceeds. During the main sequence phase, stars steadily convert hydrogen into helium, and in doing so they regulate the long-term balance between gravity, radiation, and matter in galaxies. Massive main sequence stars influence their surroundings strongly through radiation and winds, helping shape nearby clouds and future star formation. Lower mass stars preserve hydrogen-burning light over immense durations, extending the luminous era of galaxies far into the future. In both cases, the main sequence is where the relationship between raw primordial matter and organized stellar energy becomes most durable. The early universe begins largely with hydrogen and helium. The main sequence is the phase in which that hydrogen becomes sustained starlight on a vast scale. Later stages enrich the universe more dramatically with heavier elements, but the main sequence supplies the long continuity that makes stellar populations stable enough to structure galaxies over time. There is something quietly revealing in the fact that the most common stars are not the most extreme. The universe contains neutron stars dense beyond ordinary imagining, black holes that warp surrounding space and time, and supernova explosions that briefly outshine entire galaxies. Yet these are not the dominant lights of the cosmos in any steady sense. The ordinary background of galactic radiance comes instead from stars living in equilibrium, stars whose defining act is not explosion or collapse, but endurance. They hold themselves together through hydrogen fusion, maintain their structure across immense spans, and in their vast numbers fill the dark between nebulae with a more patient illumination. The drama of stellar evolution depends on exceptional moments, but the lasting brightness of the universe depends on what happens between those moments. It depends on the main sequence. That is why the phrase "most common stars in the universe" carries more weight than it first appears to carry. It does not simply mean that many stars fit this description. It means that the universe, as a visible place, is deeply shaped by a long, stable mode of stellar life. The most enduring points of light are not accidents scattered at random. They are the outcome of a common threshold crossed again and again in molecular clouds across galaxies, enough mass for hydrogen fusion, enough balance for hydrostatic equilibrium, enough time for starlight to persist. From that repeated achievement comes the broad population that fills the Hertzsprung and Russell diagram, populates the Milky Way, lights distant galaxies, and provides the stable environments around which planets may orbit. Main sequence stars are the ordinary fires of the cosmos, but ordinary here does not mean trivial, it means foundational. They are the stars most likely to exist, most likely to last, and most likely to define what a galaxy looks like when seen across the dark. In the end, the main sequence is not only a stage of stellar evolution, it is the long, bright fabric of the universe itself, woven from countless stars that shine not because they are rare, but because they are the most enduring answer matter has found to the pressure of its own gravity. The longer astronomy is studied, the more the ordinary stars begin to feel like the true architecture of the visible universe, not because they are the most violent, or the rarest, or the most difficult to imagine, but because they endure. A main sequence star is matter held in long negotiation with gravity, a balance maintained by hydrogen slowly becoming helium in a hidden core. That process is simple in outline, yet it gives rise to nearly everything that makes the stellar sky feel structured rather than scattered. It produces blue stars that burn quickly and red dwarfs that may outlast the present age of the cosmos. It gives the sun its long middle life and offers distant planets the possibility of time. It fills galaxies not with a single kind of light, but with an ordered range of them, all tied to the same deep principle. In that sense, the main sequence is less a category than a calm, recurring solution, one the universe returns to again and again whenever gravity gathers enough hydrogen and the core becomes hot enough to answer collapse with fusion. The result is not perfect stillness, but a durable kind of continuity. A star holds its shape. Light crosses space. Worlds circle in that light. Chemistry unfolds under it. And for spans far beyond any human measure, the balance continues. There is something restful in that idea. Most stars are not in their brief beginning or their dramatic end. They're in the long central interval, quietly maintaining themselves. The universe contains many extremes, but much of its visible character comes from this steadier condition, from stars that persist, and perhaps that is why the main sequence matters so much. It reminds astronomy that endurance is as important as spectacle, and that the most common lights in the cosmos are also the ones that make cosmic time feel patient